So we have many different types of networks, right? Internet, a World Wide Web, and power grid, phone calls, email, science collaboration, actor network citation, and protein inequal in metabolism, right? So when you see the average degree, so you can get some idea about their some sort of density about the network, right? So what is the most sparse data set? The email data set. Of course, we don't send emails to all the people, right? What is the most dense data set? Actor network. Because we have the limited actors and they participate the movies and so on and so on, right? And year by year they act in for their own roles in the different movies, right? Some people participate in the more than 10 movies a year, right? So that's why it is dense. It looks like very dense. 83. Maybe that information is from the active actors. So I don't know. So the data set looks like that. All right. So from the degree information, we can plot the degree distribution, right? The P of K means the probability that a randomly chosen node has the degree K. So this is the degree, right? This is a probability. So we have, in this case, this is a degree 1, 3, 2, 2, right? So we have, we can make a table something like this. This is degree. This is the count, right? 1, 2, 1. What is the probability? So in total, we have 4 possible edges, right? So 1 over 4, 1 over 2, and we have 0.25. So in this case, so this goes to this plot, and this goes to this plot, and this goes to this bar plot, right? So this is the way to plot the degree distribution. And in this connected graph in the below, they all have 2 possible edges, right? So the only possible degree is 2, and the probability equals to 1, right? So this is from a real network data set. And remember, this is from the protein-protein interaction, and it looks like the most of the data set has a very a few degrees, right? For example, this one, this represents the degree is 1. It looks like 0.48 with this probability, and is likely to have just 1 edge, right? What about this? To have 50 edges like this, so in probability it is very, very rare to have this 50 degree node, right? This represents some distribution about the edges, so that's why it is called the degree distribution. And we call this ones are hub because it connects many different nodes. So in some cases, it is useful to understand the relationship between the probability and the degree, and when we use logarithm. So when we take the logarithm to the degree and the probability, we have this linear relationship. In many cases, we can observe in the logarithm scales, they are linearly correlated each other. So, but still looking at the hubs are very different from the rest of the nodes, right? So for the degree distribution, to represent the degree, we can use discrete representation, or we can use continuous representation using the PDF, and we can normalize the sum of the probability. So usually it is satisfied to the discrete and continuous representation. So it is important to satisfy the normalization condition, right? All right. So we have talked about the difference between the undirected and directed, right? So when you read the research paper, and you firstly need to see that the input graph is directed or undirected. So depending on the type of edges, and the approach could be very different. So when you open the paper, particularly to the new paper, and you need to see that the input is directed or not, and sometimes it could be weighted. So weighted graph means even though they have some edge, in this case we just have 0 or 1, right? But it may have some weight. The degree of the connection, right? When the edge represents some metabolic reaction, and depending on the strongness of the reaction, so you may put some number between 0 to 1, right? Usually 0 to 1. In some cases, when it has more than, when the weights have more than 0.5, you just assign the discrete edge. So it depends the graph construction conditions. So that's why it is important to understand the raw data in domain knowledge. So all right. Right, so another mathematical notation to represent the graph data is adjacency matrix. So it is two-dimensional matrix. So this matrix is composed of the V by V, right? It is to represent all the possible interactions, right? For example, we have 4 number of nodes possible, right? Here the number is 4, and here number is 4. The 4 by 4 matrix. So we expect that many numbers of the 0 values, right? The 0 means they have no interaction between the corresponding positions, right? So in the deep learning, to deal with the sparsity, we often use the sparse matrix rather than the dense matrix. Why do we use the sparse matrix? Because we don't need to store all the zero values, right? Because it doesn't include any varied information. We just need to remember the meaningful information, right? The actual interaction. Right? So in the sparse matrix representation, they just store, in this case, this is a 0 to low and 0, 1, and 0, 2, 0, blah blah blah, right? This represents the index of the column and row, right? 0th low and first column, and 0th low and second column, and first low and 0th column, right? And we just need to store the location of the 1, right? When this is the weighted matrix, we just store their weight in this position, like a 0.5, 0.3, rather than just 0 or 1, right? So the space complexity wise, it corresponds to the number of non-zeros, right? For the sparse matrix. What about dense matrix? I'm sorry. Dense matrix corresponds to big O of the V square, right? This is a very dense. So, because when you load all the data to your GPU, think about it. When you have GPU, you usually have 62 gigabytes or 16 gigabytes, and when you reach, so you have 64 or and beyond, right? Usually 16 and 32. So to deal with the dense data set, you need to prepare more memory in the GPU. So that's why we try to avoid the painful situation and try to use sparse matrix. Right? Anyway, you understand what it means, right? The adjacency. It is simple. So using this information, we can compute the degree, right? How to get the degree of the node I? We just go to the ith position and sum all the components, right? This is the undirected case. So either way is fine, right? This one and this one. They are same, right? In the directed case, it will be different, right? You just follow the in or out degree information by summing up the non-zero elements in the corresponding positions, right? Okay. So you can construct this one, right? It's pretty simple. So what will be the procedure to construct a matrix to adjacency? So we can create a pseudocode, right? Maybe from for the H in the E, right? We have the source and target from E, right? And we just assign ST1, right? You need to initialize what the A is, right? And then the init A, and then for the H, for the every H, we assign just one value. So this corresponds to still corresponds to this time complexity, right? So in the real world, the data is very sparse, right? This is from the adjacency, and when they have non-zero value, depending on their weight, we use different the color scale in the, so this is the gray scale plotting, and darkest blue represents just 1, and this is black, and this is gray, right? So it seems like many zero values, right? So this is complete graph. It is impossible to see your reaction, so I hope it won't be so difficult, right? I'm try to be very slow and give you more example when you are not familiar with my explanation, and stop and take a rest and watch the video again, and let me know in the Q&A the time. That's good. All right, complete graph. Have you heard about it? Complete graph. What is your expectation? Something is complete. Do you have some complete friend? Complete friend may have many friends, right? So in this case, all the node has is every node is connected to all the other nodes. This is called complete graph, and the maximum number of links in the network can be computed this one. Hopefully you understand this. So you remember the combination, right? From the n possible choices, we choose the 2, and this is computed using this mathematical computation, and we call this is the maximum number of links. And when the degree equals to the L max, we call the graph as a complete graph. Each average degree is n-1, right? Because it is connected to all the other nodes except themselves, right? n-1. Unfortunately, most networks observed in real systems are very sparse. They are strictly smaller than the L max. In other words, we can represent the observation using this notation, right? Here is a real observation from the real network. Very sparse, right? Here we have weighted, unweighted networks. So we already talked about the concept, right? So the adjacency connection may have the flat value between 0 to 1, right? What is a bipartite graph? It's another type of graph. This is a very common graph data, right? Here we have examples. So projection U and projection V. So bipartite represents the node is divided into 2 disjoint sets. So they are disjoint set. And every link connects a node in U 2, 1 in the V. So U in this bipartite graph is connected only some of the set V, right? Not in the U. So this is called bipartite graph. So to construct the bipartite graph in the real world case, so we often utilize the properties, some sort of the common properties in U and V. Let me give you an example. So in this case, Hollywood actor network, even though the project U is from the actor, and we can define the projection V is from the movie, right? When they participate in some movie, and it is not possible to create the edge between the actor in this example, right? But in reality, they have some friendship, right? Or professional. I mean the friendship. And when they act for the same movie, they communicate a lot. They may have some edge, something like that. But in this case, the actor participates in a movie in A, in this case, and we just represent the acting record using the bipartite graph. And another example is some user and product information. So when you go to Amazon or Coupang, right, you may represent just user, the customer, and we may represent the product, right? We just go to Coupang and buy some toothbrush, and buy the bag, and buy the pencil. Oh no, pencil, right? So we don't have communication users in the Coupang, right? So in this, I mean, our own world. In reality, they may have some communication, right? In the review or in some bulletin board, but we pretend not to knowing that information. So U and V, so they are bipartite graph information.